There is a grain of dust between the stars. Not a grain in the way a beach has grains, not something you could hold or see or feel on your fingertip. It is a particle smaller than a bacterium, a few hundred atoms of carbon and silicate bonded together in the dark, drifting at a speed so slow that in a human lifetime it would barely cross the length of a city block. It has no light of its own. It floats in a space so empty that the nearest atom to it might be several centimeters away, and the nearest star might be 2 or 3 light years in any direction. It has been drifting for longer than the Earth has existed. Nobody put it there. It condensed from the outer layers of a star that died billions of years ago, a star that swelled and then shed its outer envelope into the surrounding space, releasing material that cooled and crystallized over thousands of years into grains just like this one. When that star was gone, the grain kept moving. It will keep moving long after everything we know has changed. The space it moves through is not empty in the way a room is empty when the furniture has been cleared out. It is empty in a different way, a way the body cannot feel and the eye cannot register, a vacancy so complete that measuring it requires instruments and vocabulary that did not exist until very recently. In the region between stars, there are roughly 1 or 2 atoms in every cubic centimeter of space, not molecules, single atoms, mostly hydrogen, drifting alone in the cold. The room you are in right now contains something like 27 million trillion atoms in every cubic centimeter of the air around you. Out there, in the gap between stars, 1 or 2, that ratio, 27 million trillion to 1, is the ratio between the world we inhabit and the world that makes up most of the Milky Way. Not the spectacular parts, not the nebulae glowing in telescope photographs, not the dense clusters of young blue stars, not the bright heart of the galactic center. Those are the exceptions. The rule is what the grain of dust knows: cold, slow, almost perfectly quiet, a stillness that has no equivalent anywhere in human experience. And yet the grain is not alone in any meaningful sense. Around it, at distances that take light years to cross, other stars are burning. The light from those stars is crossing the gap right now, indifferent and continuous, arriving at this grain and passing through it or scattering slightly off it and continuing outward. The grain participates in none of this. It only drifts. This is where tonight begins, not with a number, not with a discovery, not with a question designed to pull you forward, with a grain of dust in the space between stars, moving at the pace of geological time through a silence wider than anything our languages were built to describe. The Milky Way is not what it looks like from below. From the surface of the Earth, on a night dark enough, it appears as a band of pale light stretching across the sky, softer than a cloud, more permanent than weather, faintly luminous in a way that takes a moment to register. Many people have never seen it. City light fills the lower atmosphere, and the band disappears, reduced to a rumor. But from a mountain, from a desert, from any place where the sky is still dark enough for it, the band appears overhead, and the eye settles on it with a feeling that is difficult to name. Something between recognition and strangeness, as though looking at something familiar from an angle you have never tried before. That band is the disk of the galaxy, seen from inside it. We sit within the structure we are looking at. The pale light is not coming from a separate thing in the sky. It is coming from the accumulated glow of billions of stars, distributed through the flat plane of a disk we are embedded in. And because the disk is thin and we are inside it, looking in the direction of the disk means looking through more stars than looking perpendicular to it. And those stars blur together into that soft river of light. The grain of dust is part of the same disk. So is the star nearest to us. So is the sun. Everything in that band and everything that cannot be individually resolved within it is part of the same structure. A structure so large that light takes 100,000 years to cross it from edge to edge, moving at a speed that would circle the Earth 7 times in a single second. That is the width of the disk. The thickness in our region is roughly 1,000 light years. The grain of dust drifts within a structure whose dimensions resist the imagination entirely. Not because they are merely large, but because they are large in a way that has no human equivalent to borrow from. 100,000 light years, 1,000 light years thick, the grain drifts on. Tonight we are going to move outward from that grain, slowly, the way the galaxy itself moves, without urgency and without alarm. We will pass through the architecture of the disk, through the spiral structure and the quiet spaces between the arms, past the ancient clusters orbiting the halo, outward into the web of matter that contains the galaxy itself. And at the end of all that distance, we will find our way back to something simple, the same band of light, the same stillness, the same grain, still drifting, unchanged. If you are listening in a dark room, or if your eyes have already closed, let them stay closed. None of what follows requires you to be alert. The galaxy does not ask for that. It has been here for more than 13 billion years. It will wait as long as you need. We begin at the scale of a single grain of dust, moving through the cold between stars, in the disk of a galaxy that most people have never seen from a dark enough place to understand what it actually is. The light from the nearest stars is already crossing the space around it. It always has been. Long before anyone knew what the band of light was, people gave it names. In ancient Mesopotamia, scribes pressed tablets recording the positions of stars with a precision that still holds up against modern measurements. They did not have telescopes. They did not have mathematics capable of describing orbital mechanics. What they had was consistency, the patience to watch the same sky night after night, season after season, decade after decade, until the movements became predictable and the predictable became useful. The band of light crossing their sky was noted. Its position relative to the horizon changed with the seasons. That was enough to make it a calendar. In parts of Aboriginal Australia, the band was read not as a background to the stars, but as a structure in its own right, a dark river shaped by the dust lanes that interrupt its glow, winding across the sky with its own geography. Different groups saw different beings within it. The emu in the sky, traced not by connecting bright points, but by following the dark shapes between them, is perhaps the oldest known astronomical figure in the world. The band was not decoration, it was a map. In ancient Greece, the word for it became the root of the word we still use, Galaxius, Milky, from the story of a goddess whose milk spilled across the heavens when she pulled away from an infant placed at her breast without her knowledge. The myth does not match the physics, but the impulse behind it, to take something vast and make it personal, to bring the sky into the scale of a body, a relationship, a moment, that impulse is entirely human and it has not gone away. What all of these traditions share is not an explanation, but a recognition. The band of light is there. It is always there. It is part of the sky in the way the horizon is part of the sky. Not a feature you find on a particular night, but a permanent quality of the darkness itself, available to anyone who looks up from a place dark enough to receive it. The people who knew it most practically were the ones who had no choice but to read it. The Pacific Ocean is the largest single surface feature on Earth. It is wider than all the land masses combined. Crossing it in vessels built from wood and fiber and lashed together with inherited knowledge, without any instrument more precise than the trained human mind. This required a relationship with the sky that went well beyond observation. Polynesian navigators did not merely look at the stars, they lived inside a mental model of the sky, so complete that they could feel their position within it, the way a person feels their position in a familiar room, even in the dark. The band of light was part of that model. Its arc across the sky shifted with latitude. The stars embedded within it rose and set at angles that depended on where in the ocean a navigator was standing. Sailors learned the rising points of individual stars, the way a person learns the streets of a city, not by memorizing a map, but by walking them so meticulously that the knowledge moved from the mind into the body. The band of light overhead was not a mystery to them. It was infrastructure. A navigator, standing at the prow of a double-hulled canoe in the middle of the Pacific at 2 in the morning, reading the sky with the full attention of a trained mind, That person was using the same disk of light that the grain of dust drifts through. They did not know it was a disk. They did not need to. The band rose where it was supposed to rise, arced where it was supposed to arc, and set where it was supposed to set. That was the knowledge they needed, and the disk provided it faithfully, as it had for every generation before them, and would for every generation after. There is something grounding in that continuity, if you let yourself feel it. The light falling on those navigators left its source years before it reached them. Some of it decades, some of it centuries. The stars embedded in the band were burning then, exactly as they burn now, indifferent to whether the light they were releasing would reach a human eye or pass through empty space unwitnessed. It reached those eyes. It reached the scribes pressing clay in Mesopotamia. It reached the people who traced the emu in the dark lanes of the southern sky. And tonight, if the sky above, wherever you are, were dark enough, it would reach you. The disk has not moved in any way that matters on the scale of a human lifetime. The band appears at the same declination it appeared at 10,000 years ago. The stars within it have drifted slowly, over centuries. The positions have shifted enough that a navigator from ancient Polynesia, using the same star compass today, would find small errors accumulating. But the band itself, the structure of the disk, the fact that we are inside it and surrounded by it on all sides, that has not changed. The child who first looks up at the Milky Way from a genuinely dark place and does not know what they are seeing. That child is having the same first experience that every human being who has ever lived under a dark sky has had. Not an experience of astronomy, an experience of scale, of being small inside something in darkness, as being not empty but full of something faint and steady and beyond naming, at least at first. Most of us do not have that experience early. The sky is too bright where we live. The band has been hidden behind the light we make ourselves, but it is still there. The disk is still there, exactly where it has always been, holding the grain of dust and the nearby stars and the sun, and every planet that orbits it, all of them moving through the same flat structure, all of them part of the same slow rotation that has been ongoing for longer than the Earth has had oceans. The band of light is the visible edge of that. It was infrastructure for navigators. It was a calendar for scribes. It was the body of a goddess in a Greek myth. It was a dark river, alive with figures in the southern sky. Now we know it is a disk, a galaxy, a structure with a specific shape, a specific age, a specific architecture. And even with all of that knowledge, the thing it produces in a person who sees it from a dark place for the first time is still the same thing it has always produced, a quiet. A sense of something larger than the concerns of the day, present and patient, available to anyone who goes to where the sky is dark enough to receive it. The grain of dust drifts through the interior of that disk right now, as it has drifted for billions of years, as it will drift long after the last record of tonight has dissolved into nothing. The band holds its position in the dark. The disk did not arrive fully formed. Nothing in the galaxy did. What exists now? The flat spinning structure, the spiral pattern of star formation, the quiet interarm spaces, the dense bulge at the center, all of it emerged from something that looked nothing like it. The beginning was formless in a way that makes the current shape of the galaxy seem almost improbable, not designed, not inevitable, the result of physics acting on matter across a span of time so long that the word gradual fails to carry the right weight. In the early universe, not long after the first atoms formed, the cosmos was filled with gas, mostly hydrogen, some helium, traces of lithium. These were the only elements that existed. The heavier ones had not yet been made, because the only furnaces capable of making them had not yet ignited. The gas spread across the expanding universe in a distribution that was almost perfectly uniform. Almost. In that near uniformity, there were tiny variations. Regions where the density was slightly higher than the average. Regions where it was slightly lower. The differences were extraordinarily small, roughly 1 part in 100,000. If you had been able to measure the temperature of the early universe in 2 neighboring regions, the difference would have been a fraction of a millionth of a degree. By any ordinary measure, these were not meaningful differences. By the measure of gravity acting across billions of years, they were everything. Gravity does not care about the size of a difference. It cares only about whether a difference exists. The slightly denser regions pulled on the matter around them, drawing more gas toward their centers, becoming denser still. The slightly underdense regions lost material to their neighbors, thinning further. The process was slow at first, almost imperceptibly slow, but it was relentless and it had time. Over hundreds of millions of years, the overdense regions grew into enormous structures, clouds of hydrogen and helium gas, spanning distances that light would take tens of thousands of years to cross, all of it slowly contracting under the gravity of its own mass. These were the proto-galaxies. Not yet galaxies, not yet anything with a recognizable shape, but the raw material from which galaxies would eventually emerge. And they were rotating. Not because anything set them spinning deliberately, because in a universe where matter is distributed unevenly, any large clump of material will inevitably carry some net angular momentum, a slight residual spin inherited from the asymmetric distribution of mass around it. As the cloud collapsed inward under gravity, that rotation was amplified. The same principle that makes a spinning figure skater move faster when pulling their arms toward their body. As the cloud shrank, the spin accelerated. As the spin accelerated, the cloud resisted collapse in the directions perpendicular to the spin axis. It could collapse along the axis freely. Perpendicular to it, the rotation pushed back. The result was a disk, not a sphere, not a random clump, a flat, spinning structure, thinner along the axis of rotation and extended in the plane perpendicular to it. The disk shape of the Milky Way is not decorative. It is the direct physical consequence of gravity and angular momentum acting on a rotating gas cloud over hundreds of millions of years. Every spiral galaxy we observe carries the same signature: the disk, the spin, the flatness, because every one of them formed through the same process, starting from the same physics. Within the disk, the gas was not uniform. It never is. But within the collapsing cloud, created pockets of higher density, regions where the gas was compressed enough and cold enough for gravity to begin pulling it together at a smaller scale. These pockets fragmented further. The fragments collapsed. In the densest, coldest regions, what astronomers now call molecular clouds, the gas compressed until temperatures at the cores reached millions of degrees and nuclear fusion ignited. The first stars burned. They were different from the stars that exist now, far more massive, burning hotter and faster, consuming their hydrogen in millions of years rather than billions. When they died violently, in explosions that scattered their contents back into the surrounding gas. And those contents included something the original gas did not have: heavy elements, carbon, oxygen, iron, silicon, the raw material for solid things, for dust grains, for rocky planets, for the chemistry that eventually produces everything we recognize as complex. Each generation of stars enriched the disk. Each explosion seeded the surrounding gas with heavier elements that the next generation of stars inherited. The disk was not merely forming stars. It was building, slowly and without intention, the chemical conditions that would make a different kind of star formation possible. Stars with planets, planets with surfaces, surfaces where chemistry could accumulate complexity over geological time. In ancient Egypt, a scribe watching from a rooftop in the delta would have seen the band of light crossing the same sky, with the same stars embedded in it, in very nearly the same positions. The geometry has not changed on any timescale a civilization can perceive. He did not know he was looking at the edge of a disk. He did not know the disk had been built from collapsing gas over billions of years, or that the stars in it were the product of successive generations of nuclear burning and explosive death. He knew the band was there, that it moved across the seasons, that it had been noted by people before him, and would be noted by people after him. The disk was already 10 billion years old when he looked at it. It had already run through multiple generations of star formation, already seeded itself with heavy elements, already settled into the shape we would recognize today. The scribe was looking at a finished thing, or as finished as something that is still slowly forming new stars, still slowly consuming its gas, still slowly rotating, can be said to be finished. The star formation process that built the disk is not efficient. This is worth sitting with, because it changes how the galaxy looks when you understand it. Only the coldest, densest regions of the gas, the molecular clouds, are capable of collapsing into stars. And even within those clouds, only the densest cores actually complete the collapse. Surrounding material is too warm, too turbulent, too supported by magnetic fields threading through it to fall inward. When stars do form, they immediately begin destroying the conditions that made their formation possible. Their radiation heats the surrounding gas, their stellar winds push it outward, their eventual deaths in supernova explosions disperse whatever molecular cloud remains. Stars form in isolated pockets and then clear the space around them. The efficiency of this process, the fraction of a cloud's mass that actually becomes stars, is somewhere between 1 and 3%. 1 to 3%. For every 100 units of gas in a molecular cloud, 97 or more will drift back into the interstellar medium without ever forming a star. The material that becomes a sun, that becomes a planet, that eventually becomes the surface of a world where something looks up at the disk. That material represents a tiny exception carved out of an enormous norm of diffuse, unformed gas. The disk is mostly what never collapsed. The stars embedded in it are the exceptions, the specific pockets where conditions came together in exactly the right way, at exactly the right time for gravity to win. Between those pockets, the gas that did not collapse drifts on, cold and thin, 1 or 2 atoms per cubic centimeter, carrying the grain of dust through a silence that has been accumulating since before any of the current stars were born. The disk formed from formlessness. It built its stars from the rarest of conditions. It spent billions of years enriching its own gas with the elements that make solid things possible. And then it waited for someone to look up at the band of light it produces and wonder where it came from. The wondering started a long time ago. The disk had already been at work for most of the age of the universe, before the first human eye registered the pale glow crossing the dark sky, and felt the particular quiet that comes from looking at something larger than any frame available to hold it. That quiet is still available. It is what the disk has always produced in anyone who goes somewhere dark enough to receive it. The grain of dust drifts through the interior of that disk, through one of the regions where the gas never quite collapsed, past stars that formed in other pockets long ago, and are now simply burning steadily through the long middle of their lives. Everything is still. The disk continues its slow rotation, as it has for more than 10 billion years, carrying everything within it in the same direction at the same measured pace, the way a river carries everything in it. Without urgency, without preference, simply because that is what the physics requires. The disk is not uniform. From a distance great enough to see it whole, from a position hundreds of thousands of light years above the galactic plane, looking down at the flat spinning structure from outside, the Milky Way would reveal itself as a barred spiral galaxy, a central bulge of old, densely packed stars, a bar of stars extending from that bulge in 2 directions, and from the ends of the bar, curving outward and trailing in the direction of rotation, the spiral arms, long, luminous, slightly thicker with gas and young stars than the spaces between them. The spiral pattern is one of the most recognizable shapes in astronomy. It appears in galaxies across the observable universe, produced by the same physics, operating on the same basic ingredients. But the shape is deceptive in a specific way that matters for understanding what the disk actually contains. The spiral arms are not solid structures. They are not walls of matter that stars pass through and stay within. They are waves, density waves, moving through the disk the way a ripple moves through water. The water does not travel with the ripple. It rises and falls as the wave passes through, then returns to where it was. The stars in the disk do not travel with the spiral arms either. They orbit the galactic center at their own speeds, occasionally passing through the higher density region of an arm and then continuing on into the space between arms. What makes the arms bright is not that they contain dramatically more stars. It is that they contain more gas, and where there is more gas, there is more star formation, and where there is more star formation, there are young massive stars, and young massive stars burn hot and blue and emit thousands of times more light than older, dimmer stars. A single massive young star can outshine 1 million red dwarfs. The arms glow because of those bright young stars, not because stars are genuinely packed more tightly there. Our Sun is not currently inside a major spiral arm. It sits in a smaller feature called the Orion Spur, a partial arm, a bridge of gas and young stars connecting two of the Milky Way's larger arms. In cosmic terms, we are in the interarm region, the quieter space between the main zones of active star formation. The stellar density here is lower than in the arms. The radiation environment is calmer. The probability of a nearby supernova disrupting the solar system is smaller than it would be in the dense, active environment of a major arm. The grain of dust drifts through this same quiet region. Here, in the interarm space, the interstellar medium is thin even by its own standards. The gas is present, 1 atom per cubic centimeter on average, sometimes a little more, sometimes a little less. But it is not compressed into the cold, dense pockets that trigger star formation. It is warm enough and diffuse enough to simply persist, cycling slowly through the galaxy without ever crossing the threshold that would cause it to collapse into something new. The local bubble is part of this picture. Tens of millions of years ago, a cluster of massive stars in our region of the disk lived their brief, brilliant lives and died in a series of supernova explosions. Each explosion drove a shock wave outward into the surrounding interstellar medium, heating the gas and pushing it away from the center of the blasts. Over time, the overlapping shock waves carved a cavity in the interstellar medium, a region of gas hotter and thinner than the surrounding disk, extending several hundred light years in multiple directions from the site of the explosions. The solar system is inside that cavity. The local bubble, as it is called, is an old scar left by stars that no longer exist, a region of slightly emptier space within the already nearly empty interstellar medium, and we have been moving through it for somewhere in the range of a few million years. The boundary of the bubble is marked by a thin shell of denser gas where the original shockwaves swept up material and piled it at the edges. Beyond that shell, the interstellar medium resumes its normal character. At the center of the entire disk, far from the quiet interarm region where the grain of dust drifts, is something different in kind. The galactic center is not accessible in visible light. Between here and there, roughly 26,000 light years of interstellar medium lies along our line of sight, and within that medium there is enough dust, particles, not unlike the grain we began with, to absorb essentially all of the visible light coming from that direction. The galactic center is behind a curtain. Radio waves and infrared light pass through the curtain more easily, and it is through those wavelengths that astronomers have mapped what lies behind. What lies behind is a dense, ancient, crowded region unlike anything in our local neighborhood. The galactic bulge, the swelling at the center of the disk, is packed with old stars, stars that formed in the early universe when the galaxy was young and star formation was rapid and intense. These stars are not young blue giants. They are old, red, cool, burning slowly through the last of their hydrogen, many of them as old as the galaxy itself. The stellar density in the bulge is orders of magnitude higher than in our interarm neighborhood. The average spacing between stars, which is 4 to 5 light years in our region, drops to fractions of a light year in the densest parts of the bulge, and to light weeks or light days in the innermost regions near the galactic core. Even there, the stars are not close by any human measure. A light week is the distance light covers in 7 days of continuous travel, roughly 113 billion miles. That is the gap between neighboring stars at the center of our galaxy at their most closely packed. A distance so vast it has no analogy in human experience. And yet by galactic standards, it represents something approaching crowded. At the center of the bulge, at the precise gravitational heart of the disk, is Sagittarius A. It is a black hole. Not the largest known. There are black holes in other galaxies, orders of magnitude more massive, but a genuine supermassive black hole, roughly 4 million times the mass of the Sun, compressed into a region smaller than our solar system. Its presence has been confirmed not by observing it directly, but by watching the stars that orbit it. Individual stars have been tracked for decades in their orbits around the galactic center, their paths curving and accelerating as they approach and then swing away from an object whose mass is precisely calculable from those paths. One of those stars, designated S2, passes close enough to Sagittarius A that at its nearest point, it moves at roughly 2% of the speed of light. Not 2% of the speed of sound, 2% of the speed of light, approximately 13,000 miles per second. A star moving that fast in an elliptical orbit around an invisible mass at the center of the galaxy. The orbit takes roughly 16 years to complete. Astronomers have watched it complete more than one full circuit. The black hole does not announce itself. It does not glow. It does not radiate in any way that makes it visually obvious. Its presence is inferred entirely from the behavior of the matter around it. Light that passes too close to it does not escape. Material that falls into it releases energy as it spirals inward, producing radiation detectable in X-ray and radio wavelengths. But the object itself is defined by the absence of signal, a place where information stops being transmitted, where the physics we use to understand everything else breaks down at the boundary. It has been at the center of the disk for most of the galaxy's history. Everything in the disk orbits it, in the sense that everything in the disk orbits the collective mass of the galactic center, the black hole, the dense population of stars in the bulge, the dark matter concentrated at the core. The Sun takes roughly 225 million years to complete one orbit. In the 4.5 billion years since the solar system formed, the Sun has completed approximately 20 of those orbits, slowly tracing its path around the center of the disk, while everything else in the disk does the same. The interstellar medium fills the spaces between all of it, between the stars in the bulge and the stars in the arms, and the stars in the interarm regions, and the ancient stars in the halo above and below the disk. It is not the same everywhere. Near hot young stars, the radiation ionizes the surrounding gas, stripping electrons from atoms and producing vast glowing regions of plasma, the nebulae that appear in telescope photographs as bright clouds of color. Farther from those heat sources, the gas is cooler and neutral. In the coldest, densest pockets, hydrogen atoms tear into molecules, and the temperature drops low enough for the dust grains like the one we began with, to accumulate icy coatings of water and carbon compounds. Each phase of the interstellar medium has its own character, its own temperature, its own density. Together, they form a layered, complex environment that is always in motion, always being stirred by the energy output of stars, always cycling material from diffuse gas to dense cloud to star and back again over timescales of millions of years. Right now, as you are resting, light is crossing the local bubble, light that left a star several hundred light years from here, years or decades ago, traveling at the only speed it knows how to travel, crossing the thin hot gas of the bubble's interior without slowing, that is arriving in this moment, not in a moment that is approximate or representative. This specific moment, while you are still, while the room is quiet, while everything feels paused, the light is completing its crossing. The disk does not pause, it continues its slow rotation. The gas drifts, the dust grains move, the stars burn through their hydrogen at rates determined by their mass. The spiral arms turn more slowly than the stars within them, passing through the disk like a long, slow wave. while individual stars drift in and out of them over millions of years. The galactic center holds its position. Sagittarius A waits at the center of everything, as it has waited for billions of years, neither growing nor shrinking in any meaningful way, simply present at the gravitational heart of the structure. The grain of dust, far from all of that, in the quiet interarm region, continues its drift. It does not know about the bulge or the arms or the black hole at the center. It drifts through a very local experience, a cubic centimeter of space, the nearest atom a few centimeters away, the nearest star a few light years in some direction. That is the whole of its world. The rest of the disk exists, enormous and intricate, entirely beyond the scale at which a grain of dust has any relationship with anything. But we are not a grain of dust. We can hold the entire disk in mind, the bar and the arms and the bulge, and the quiet interarm regions and the interstellar medium cycling through all of it, and still return to the grain, still locate ourselves within the structure, still feel the quiet of the region we happen to occupy. The disk is vast, our piece of it is still. Both things are true, and neither cancels the other. The disk is not the whole of it. Step back far enough, not in imagination only, but in the careful outward movement of scale that astronomy makes possible, and the galaxy reveals itself as a smaller thing than it appeared from inside. Not small, nothing about it is small, but bounded, surrounded, part of a larger arrangement that it did not choose and cannot leave. Above and below the disk, extending in every direction far beyond the flat plane of stars and gas, is the galactic halo. It is not empty, though it is close. Old stars drift through it on wide, tilted orbits that carry them far from the disk, and then back again over timescales of hundreds of millions of years. These are among the oldest objects in the galaxy. Stars that formed in the first billion years after the universe began, before the disk had settled into its current shape, when the galaxy was still a chaotic forming thing. They carry in their compositions a record of a time when heavy elements were rare, when the interstellar medium had not yet been enriched by successive generations of stellar death. They are the galaxy's oldest witnesses, and they orbit in the halo like slow satellites, tracing paths that have nothing to do with the disk's flat rotation. Among them, orbiting at large distances from the galactic center, are the globular clusters. There are roughly 150 of them associated with the Milky Way. Ancient, dense, roughly spherical collections of stars, each containing anywhere from a few 100,000 to several million stars packed into a region, only a few dozen to a few hundred light years across. They are among the oldest structures in the galaxy, some of them formed before the disk existed. They have been orbiting the galactic center ever since, on paths that carry them through the halo and occasionally down through the disk, emerging on the other side and swinging back out into the halo again on timescales of hundreds of millions of years. The largest of them, Omega Centauri, contains roughly 10 million stars in a region about 150 light years across. From inside Omega Centauri, from a planet orbiting one of its inner stars, if any such planets exist, the night sky would be extraordinary, not because there would be drama or violence, but because there would be light. Thousands of stars visible at brightnesses that have no equivalent in our own sky. The nearest stellar neighbors not 4 or 5 light years away, but fractions of a light year. The darkness between stars would be less dark. The sky would never go fully black. Omega Centauri may not be a true globular cluster at all. Some astronomers believe it is the stripped core of a small galaxy, a dwarf galaxy that fell into the Milky Way's gravitational influence long ago, had its outer stars pulled away by tidal forces over billions of years, and left only its densest central region behind. If that is what it is, then what we see as a globular cluster orbiting our galaxy is actually the heart of something that was once a separate structure, consumed and absorbed, its identity dissolved into our own. The halo holds other things as well. Satellite galaxies, small, dim, gravitationally bound companions to the Milky Way, orbiting it at varying distances. The large and small Magellanic Clouds are the most visible of these from the southern hemisphere, close enough and large enough to appear as detached patches of the band of light on a dark night. Farther out, dozens of smaller dwarf galaxies have been identified, some of them so diffuse and so faint that they were not discovered until the era of sensitive modern sky surveys. They orbit the Milky Way the way the Milky Way orbits the galactic center, in paths shaped by gravity, patient and slow, on timescales that dwarf anything else we have discussed. Beyond the halo, the Milky Way is not alone. It sits within the local group, a collection of roughly 80 galaxies, most of them small, gravitationally bound to one another across a region of space, approximately 10 million light-years across. The Milky Way and Andromeda are the two largest members, each surrounded by their own retinues of satellite galaxies, each containing hundreds of billions of stars, each embedded in dark matter halos that extend far beyond their visible disks. Andromeda is 2.5 million light-years away. On a clear night, from a dark location in the northern hemisphere, it is visible to the naked eye, the most distant object a human can see without any instrument. A faint smudge near the constellation of Cassiopeia. The light arriving at the eye, right now, left Andromeda 2.5 million years ago, in an era when the ancestors of human beings were walking upright on the African savanna, but had not yet begun making stone tools. The galaxy was already formed then. The light has been traveling ever since. Every generation of every human civilization that has ever existed has been alive while that same light was in transit. It was crossing the intergalactic gap while the pyramids were built, while Rome rose and fell, while the first telescopes were pointed at the sky. The light that reaches the eye tonight began its crossing before any of that, and has outlasted all of it. The local group is itself not the end of the structure. It is a small cluster on the edge of a much larger arrangement, the Laniakea supercluster, a vast gravitational basin containing roughly 100,000 galaxies distributed across a region of space, approximately 520 million light-years across. Laniakea was only mapped as a coherent structure in 2014, when astronomers developed techniques for tracing the flow of galaxies through space toward their gravitational attractors. What emerged from that analysis was a picture of our cosmic neighborhood at a scale that had not been clearly resolved before. Not just the local group, not just the nearest galaxy clusters, but the full extent of the gravitational basin within which the Milky Way and its neighbors are slowly moving. At the center of Laniakea, toward which everything within it is drifting, is the Great Attractor, a region of unusually high mass concentration about 250 million light-years from us, its precise nature still partially hidden behind the plane of our own disk. The Milky Way is moving toward it at approximately 600 kilometers per second. Not because anything is pulling it urgently, because the gravitational landscape of the supercluster tilts in that direction, and over billions of years, everything tilts slightly downhill. And then, beyond Laniakea, is the cosmic web. The web is the largest coherent structure in the observable universe. Matter is not distributed randomly across the cosmos. It is organized into a pattern, long filaments of galaxies and galaxy clusters stretching for hundreds of millions of light-years, intersecting at dense nodes where the largest concentrations of galaxies accumulate, with enormous voids between the filaments where the density of matter drops to near nothing. The voids are not small. They are hundreds of millions of light-years across. They occupy roughly 80% of the universe's total volume. 80%. The filaments and walls and galaxy clusters, all of the structure, all of the galaxies, all of the stars, all of the planets, everything we have ever observed or imagined, occupy roughly 20% of the universe's volume. The rest is the voids, cold, dark, nearly empty, with individual galaxies scattered sparsely through them, but nothing like the concentrations found in the filaments. The web grew from the same density fluctuations that built the galaxy. Those fluctuations existed at every scale simultaneously, not just at the scale of individual star-forming clouds, but at the scale of galaxy clusters, of superclusters, of the largest structures the universe contains. gravity amplified the density differences at every scale. Where matter was slightly more concentrated, it pulled in more matter. Where it was slightly less concentrated, it lost matter to its neighbors. Over billions of years, this process organized the universe's matter into the web, a structure that no single mind can hold in full, that no instrument has yet mapped completely, that extends in every direction to the edge of what we can observe and presumably far beyond. The Milky Way sits in a filament of this web, in the local group, in the outskirts of the Laniakea supercluster, in a region of space that is neither the densest nor the most empty, somewhere in the middle of the cosmic hierarchy, a position that may not be coincidental. Every generation that has looked up at the band of light crossing the sky has been looking at one thread of one filament, of one structure in a web that spans the observable universe. They did not know that. The navigators reading the sky for star bearings did not know that. The scribes pressing clay tablets did not know that. The child who sees the band of light for the first time and feels the quiet that comes from looking at something larger than any available frame. That child does not know that either. The knowing does not change the quiet, it deepens it, because every one of those generations and every person who has ever looked up from a dark enough place was participating in the same thing, a small concentration of matter, organized temporarily into something capable of perceiving the structure around it, looking outward into a web of matter and emptiness that had been building itself for almost 14 billion years before any eye existed to receive it. The band of light overhead is one edge of the disk. The disk is one galaxy among roughly 2 trillion in the observable universe. Most of what exists between all of them is the void, patient, cold, and so vast that the word vast is insufficient, and threading through all of it, through the disk and the halo and the local group and the supercluster and the web and the voids is something that no telescope has ever directly seen, but that every measurement of galactic structure requires to be there. Dark matter. The Milky Way's dark matter halo extends approximately 600,000 light-years from the galactic center, 6 times the diameter of the visible disk. It does not emit light. It does not absorb light. It does not interact with the electromagnetic spectrum in any way that current instruments can detect. It is present only in its gravitational effects, in the way the disk rotates faster at its edges than it should, if only the visible matter were providing the gravity, in the way the satellite galaxies orbit at distances and speeds that require far more mass than the stars and gas alone can account for. The dark matter is most of the mass of the galaxy. The stars, the hundreds of billions of stars burning through the disk and scattered through the halo, all of that visible, luminous, nuclear burning matter, represent a fraction of the total. The galaxy is mostly something we cannot see, distributed through an enormous sphere centered on the galactic center, providing the gravitational scaffolding within which the disk and its stars exist. We live in the visible part of an invisible structure. The band of light overhead is the luminous surface of something far larger, far more massive, and almost entirely dark. It glows because of the stars within it. But those stars are floating within a gravitational architecture that is mostly dark matter. Matter that has been present since the early universe, that shaped the formation of the galaxy, that holds it together against the tendency of its own rotation to disperse it. Every grandmother who pointed upward at the band of light on a summer night, every child who asked what it was, every navigator who used it as a landmark across open water, all of them were standing within the visible edge of something mostly invisible, looking at the part of the galaxy that happens to emit light, surrounded on all sides by a vast dark structure that neither glows nor reflects. The knowing changes nothing about the pointing. The sky is still there. The band is still there. The quiet is still available to anyone who goes somewhere dark enough to find it. What changes is the depth of the darkness around the light, and how much of what we cannot see turns out to be holding everything we can. The galaxy will not always look like this. Nothing holds its current shape indefinitely. The disk turns. the gas slowly depletes. The stars that exist now are burning through fuel that cannot be replenished. Hydrogen fusing into helium in stellar cores across the galaxy, the helium accumulating, the hydrogen fraction declining imperceptibly slowly on any human timescale, but steadily and without reversal on the timescale of the galaxy itself. The first change that is coming is also the largest. Andromeda is not staying where it is. It has been approaching the Milky Way for most of the age of the universe, drawn by the mutual gravity of two large galaxy clusters that cannot remain separated indefinitely. Currently, it is closing at roughly 246,000 miles per hour. That sounds fast. It is fast by any human measure. At that speed, a journey from the Earth to the Moon would take about 3 seconds, but Andromeda is 2.5 million light-years away, and even at that closing speed, the approach takes time. In roughly 4 billion years, the two galaxies will begin their interaction. Not a collision in the way two solid objects collide, not an impact, not a crash, not a destruction. The Milky Way and Andromeda are both mostly empty, mostly the space between their stars, mostly the thin interstellar medium, mostly dark matter halos extending hundreds of thousands of light years from their centers. When the two structures meet, they will interpenetrate. Their dark matter halos will begin to overlap and merge. Their interstellar media will collide, and unlike the stars, gas can interact directly, can compress, can heat, can trigger new bursts of star formation as the two gas reservoirs slam together and compress into new molecular clouds. The stars themselves will not collide. This seems wrong at first. Two galaxies merging, hundreds of billions of stars in each, and yet virtually no individual stars will physically strike another. The reason is the same emptiness we have been tracing throughout the disk. The stars are so far apart relative to their sizes that even during a full galactic merger, the probability of two stars occupying the same space at the same time is negligibly small. The stars of Andromeda will pass through the stars of the Milky Way the way two swarms of widely spaced particles pass through each other. Close approaches will happen. Gravitational interactions will disturb orbital paths. Some stars will be flung outward into intergalactic space. On hyperbolic trajectories they will follow forever. But physical contact between stars will be extraordinarily rare. What the merger will produce is not destruction, but rearrangement. The two disks will pass through each other, drawn apart by their momentum, then fall back together again under gravity, then pass through again, oscillating and interpenetrating over a period of hundreds of millions of years. With each pass, tidal forces will distort both galaxies, pulling long streams of stars, tidal tails, out into the space between them. The spiral structure of both galaxies will be disrupted. The orderly flat disks that exist now, built over billions of years of gradual settling, will be scrambled into something more chaotic, more three-dimensional. Eventually, after enough passes, the two galactic centers will spiral toward each other. The supermassive black holes at the heart of each galaxy, Sagittarius A at the center of the Milky Way, and the equivalent mass at the center of Andromeda, will begin their own long spiral inward, taking perhaps another billion years after the initial interaction begins to finally merge. When they do, the energy released in gravitational waves will be extraordinary by any measure, though it will produce no explosion visible to the eye. Gravitational waves pass through matter without interacting with it the way light does, carrying their energy silently outward through space. What remains after all of this is something astronomers call Milkomeda, a working name for the merged galaxy, which will be neither spiral nor disk, but something more like an elliptical galaxy. The grand spiral structure that makes the Milky Way recognizable in photographs will be gone. The flat disk, the bar, the curving arms, all of it will have been randomized by the interaction into a roughly spherical distribution of stars orbiting a common center. The gas reservoirs of both galaxies will have been largely consumed in the burst of star formation triggered by the merger. New stars will have formed and burned and died. The merged galaxy will be older, quieter, its star-forming activity slowed. The Sun will still exist during the early stages of this interaction. 4 billion years from now, the Sun will be near the end of its hydrogen-burning phase, beginning to swell into a red giant. Whether the solar system survives the merger is not certain. There is a small but non-zero probability that a close encounter with another star during the interaction could disrupt the outer planets, or that the Sun itself could be one of the stars flung outward. But the probability of dramatic disruption is low. The solar system may drift through the entire merger relatively unmolested, carried along by the same gravitational dance that shuffles billions of other stars. After the merger, after the star-forming burst triggered by the collision of gas reservoirs has run its course, the new galaxy will settle into a long quietude. The star formation rate will decline. The remaining gas, most of it consumed in the merger-triggered burst, will thin further. New stars will form more rarely, at intervals growing longer as the reservoir depletes. This decline is not unique to the Milkomeda merger. It is a direction the galaxy is already moving in, slowly and without drama. The star formation rate of the Milky Way has been declining for billions of years. The peak of star formation in our galaxy, the era when molecular clouds were most abundant, when new stars were igniting most rapidly, occurred roughly 10 billion years ago. Since then, the rate has been declining, not sharply, not catastrophically, slowly, the way a fire settles when there is less fuel to feed it. The existing stars will outlast the decline. The most massive ones are already gone. They burned through their fuel in millions of years and died long before the solar system formed. Medium-mass stars like the Sun burn for roughly 10 billion years. The Sun has about 5 billion years remaining. But the most numerous stars, the red dwarfs, small and cool and extraordinarily frugal with their fuel, will burn for far longer than either. A red dwarf of the smallest known mass burns its hydrogen so slowly that it can persist for several trillion years before exhausting its fuel. Several trillion years. The current age of the universe is roughly 14 billion years. A small red dwarf star can remain burning for hundreds of times that span, long after the Andromeda merger has completed, long after the merged galaxy has settled into its elliptical shape and star formation has slowed to nearly nothing, long after the last large star has burned out and the night sky of any surviving world has dimmed to a much sparser arrangement of faint red points. Eventually, even the red dwarfs will exhaust their fuel. They will not explode. Stars below a certain mass do not have the core conditions necessary for a supernova. They will simply swell slightly toward the end, shed their outer layers, and leave behind a white dwarf, a dense, slowly cooling remnant no larger than the Earth, containing roughly the mass of the Sun, radiating the last of its stored heat into the surrounding space. With no ongoing nuclear reactions, the white dwarf will cool over an enormous span of time, billions and eventually trillions of years, toward the ambient temperature of space. The disk will dim, not suddenly, not on any timescale that would be noticeable from 1 century to the next, or from 1 millennium to the next, or even from 1 million years to the next, but on the timescale of trillions of years. The brilliant disk of stars that the ancient navigators used to find their way, and the scribes has catalogued, and the child stared up at from a dark meadow, that disk will fade. The band of light will grow dimmer as the stars within it burn out. The halo will empty of its old stars as they reach the ends of their long lives. The galactic center will still hold Sagittarius A at its heart, waiting in the dark. The galaxy is not dying, it is aging. There is a difference. Aging is the natural consequence of time, acting on a system that began with finite fuel and has been spending it for 13 billion years. The spending has been productive. It built the heavy elements. It seeded planetary systems. It created the chemical conditions for complexity. But it is spending, not accumulating. The galaxy has been consuming its inheritance since it formed, and what it has built with that consumption is everything we see and everything we are. For now, the disk is still burning. Hundreds of billions of stars in the flat plane of the galaxy, carrying on the nuclear burning that has been ongoing since the first of them ignited, seeding the interstellar medium with the heavy elements the next generation of stars will inherit, lighting the band of light that appears overhead on a dark night and produces in anyone who sees it that quality of quiet that has no other name. The grain of dust drifts through all of it, through the current disk, through the future that is coming, through a timescale on which nothing that currently exists will remain unchanged. It does not hurry. It has never hurried. The disk turns beneath it in its long, slow rotation, carrying everything within it in the same direction, and the light from the stars crosses the space between them and arrives wherever it arrives, indifferent and continuous as it always has. There is a question underneath all of this that the facts alone do not answer. Not a question about the physics. The physics is clear enough. Gravity, angular momentum, nuclear burning, the slow depletion of gas across billions of years. Those mechanisms are well understood, or at least well described. The question underneath them is something different. It concerns the relationship between the emptiness and the existence of anything capable of noticing it. The Milky Way is overwhelmingly empty. We have traced that emptiness at every scale, from the space between atoms in the interstellar medium, to the light years between individual stars, to the hundreds of thousands of light years of the dark matter halo, to the voids that occupy 80% of the universe's volume. At every scale, emptiness is the dominant condition. Matter is the exception. Organized matter, complex enough to sustain chemistry, to hold a planet together, to support the slow accumulation of biological complexity, is an exception within the exception. And yet, the emptiness is not incidental to the existence of that organized matter. It is one of the conditions that made it possible. Our position in the interarm region of the disk, the quiet space between the active zones of star formation, means that the solar system has spent its entire existence in one of the calmer radiation environments the galaxy offers. Massive stars, the ones whose deaths produce supernova explosions, capable of bathing nearby planetary systems in lethal doses of high-energy radiation, are concentrated in the spiral arms. Out here, between the arms, they are less common. The probability of a nearby supernova disrupting the chemistry of a planetary surface over any given span of 1 million years is lower here than it would be deeper in an arm. Not zero, but lower. The spacing between stars, those 4 or 5 light years of empty space between neighboring stellar systems, means that close gravitational encounters between star systems are extraordinarily rare. A passing star close enough to significantly disrupt the orbits of the outer planets in our solar system has not happened in the 4.5 billion years of the solar system's existence, and is not expected to happen for a very long time. That stability is a gift of the emptiness. If the stars were 10 times more densely packed, if the average spacing were half a light year rather than 4 or 5, the frequency of disruptive close encounters would be dramatically higher. Planetary systems would be jostled more often. Long-term orbital stability, the kind that allows a planet to maintain consistent conditions for billions of years, would be harder to achieve. Complex chemistry takes time, not millions of years, billions. The process that produced the first self-replicating molecules on Earth, and the further process that built those molecules into cells, and the further process that organized those cells into multicellular organisms, and the further process that eventually produced nervous systems and brains. That entire sequence required something close to 4 billion years of consistent conditions on a stable planet, orbiting a stable star in a stable region of the galaxy. Take away the stability at any level, and the sequence may not complete. The emptiness provided the stability, not intentionally. Emptiness has no intentions, but the physical consequence of stars being widely spaced, of our region, of the disk being quieter than the arms, of the galaxy having the structure it has, the consequence is that here, in this specific location, the conditions for a very long, very slow, very improbable process were maintained long enough for the process to complete. There is something worth sitting with. in that if you let it settle without pressing it too hard. Not a conclusion, not a lesson, just a noticing. The child who first looks up at the Milky Way from a genuinely dark place and feels the quiet that comes from seeing something larger than any available frame. That child is standing on the product of 4 billion years of uninterrupted planetary stability. The stability was made possible by the emptiness of the region. The region's emptiness is a consequence of the way stars form, in isolated pockets, inefficiently, with enormous spaces between them that are the norm rather than the exception. The quiet the child feels looking up is related, in a physical sense, to the quiet of the interarm region the solar system has been drifting through for its entire existence. Both are expressions of the same emptiness, the one overhead vast and visible, the one around the solar system, invisible but present, holding the planetary orbit stable across geological time. Perhaps that is the deepest thing the galaxy offers to anyone who looks at it carefully enough. Not mystery, not alarm, not the vertigo of scale, though the scale is real and the vertigo is understandable. Something quieter than any of those. The recognition that the emptiness is not a failure of the universe to fill itself. It is the condition under which something brief and intricate and capable of looking upward could exist long enough to do the looking. The disk holds the grain of dust. The grain of dust drifts through the emptiness. The emptiness holds the solar system stable. The solar system produced a planet where the long, slow process completed. And somewhere on that planet, on a night dark enough, a person lies down and looks up at the band of light crossing the sky and feels something that is difficult to name, a quality of stillness, a sense of being inside something enormous and patient, a feeling that the darkness is not empty, but full of something that does not require a response. That feeling is not wrong. It is, in a quiet way, accurate. The disk is patient. It has been patient for 13 billion years. It will be patient for trillions more, dimming slowly as the stars within it burn out, carrying the last of its light across the long future the way it has always carried it, without urgency, without direction, simply because that is what light does when there is nothing to stop it. The emptiness does not end, but inside the emptiness, held briefly by the conditions the emptiness makes possible, something looks up at the band of light and rests in what it sees. That is enough. It has always been enough. The grain of dust is still there. It has been drifting through the entire length of this night, through the disk and the halo and the web and the deep future and the quiet recognition of what the emptiness makes possible, and it has not moved in any way that could be measured against the scale of what we have covered, a fraction of a millimeter perhaps in the direction it was already traveling when we began. The space around it is unchanged, 1 or 2 atoms per cubic centimeter. The nearest star still light years away in some direction, the disk still rotating beneath it at the same pace it has maintained for billions of years. Nothing about the grain has been altered by the journey. That is the nature of the scale we have been moving through. Human attention can cover it in a night. The grain requires billions of years to cross anything worth measuring. Both things are true simultaneously, and neither is more real than the other. The journey and the stillness coexist without contradiction. The band of light is still overhead. Not the same photons that were there when the navigators read the sky for their bearings. Those photons crossed the gap between star and eye thousands of years ago, were absorbed, scattered, converted into warmth, dispersed into the surrounding air without a trace. New photons are arriving continuously, have been arriving continuously for as long as the disk has had stars to produce them. The band is a river in that sense, not the same water, never the same water, but always a river, always arriving at the same place in the sky, with the same patient constancy. The navigator, standing at the prow of the canoe, read that river. The scribe on the rooftop in the delta noted its position against the horizon. The child who looked up for the first time and did not know what they were seeing felt something before they could name anything. All of them received the same continuous arrival. All of them stood within the disk they were looking at, surrounded on all sides by the structure they were only partially seeing. Nothing has changed about that since. The disk is the same disk, older, by whatever small increment of time has passed since anyone first looked at it and wondered what it was, but not meaningfully different. The same stars burn in the same arms. The same quiet interarm region holds the same sparse interstellar medium. The same dark matter halo extends in every direction beyond the visible edge of the disk, providing the gravitational structure within which everything else persists. The band of light appears overhead tonight for anyone who is somewhere dark enough to receive it. Not a different band, the same one the Navigators used, the same one the scribes catalogued, the same one that produced and continues to produce in anyone who sees it from a dark enough place. That quality of quiet that has no other name. The sense of being inside something patient and enormous, something that does not require a response, something that is simply there. The grain drifts through the interior of that same structure. It will drift through it long after every current observer has been replaced by other observers or by no observers at all. It does not require observation. It drifts in the dark as it has always drifted, unaffected by whether anyone is tracking its position or thinking about its nature or following its slow path through the cold interstellar medium. There is a constancy in that which is difficult to locate in words, not comfort in the way warmth is comfort, or rest in the way sleep is rest. Something more structural than either. The constancy of a thing that has been ongoing for longer than anything else we know, and will continue for longer than anything we can clearly imagine. The disk has been rotating for 13 billion years. The grain has been drifting for several billion of those. The light has been crossing the space between the stars for as long as the stars have existed. None of it depends on being noticed, and yet is noticeable. The band is visible from the surface of the Earth on a clear enough night. The grain is real, physical, drifting through a space that is also real and physical. The rotation of the disk is measurable. The dark matter halo, though invisible, leaves its signature in every star's orbital velocity. Everything we have moved through tonight is present and actual and available, not as metaphor, not as consolation, but as the literal structure of the galaxy we're part of. The Navigators who read the band did not have this knowledge. They had something different, a relationship built from necessity and practice and inherited understanding that was precise in its own register, accurate for what it needed to accomplish. They looked up at the same structure and extracted from it exactly what they needed. A bearing, a latitude, a confirmation that they were where they believed themselves to be. We look up at the same structure and extract something different, not a bearing, not a latitude, something harder to name, a sense of position that is not navigational but existential. Not where are we in the ocean, but where are we in the thing that contains everything. The answer the disk offers is the same answer it has always offered to everyone who has ever looked at it carefully enough to feel it rather than simply see it. You are here, inside this, part of the same structure the grain of dust drifts through, part of the same rotation that has been ongoing since before the Earth existed, part of the same disk that produced the band of light held overhead and the dark matter halo surrounding it, and the ancient globular clusters orbiting at the edges, and the quiet of the interarm region, and the light arriving from Andromeda 2.5 million years after it left. The disk does not distinguish between any of the things within it, the grain, and the star, and the planet, and the person looking up. All of it is the disk. All of it is carried in the same rotation. All of it receives the same light from the same stars, crossing the same emptiness. The band is still overhead. The grain is still drifting. The disk continues its slow rotation, as it has for 13 billion years, as it will for billions more, patient and constant in a way that no individual thing within it can be, but that the structure itself maintains across all of it, through all of the change and the dying and the forming and the long future dimming that is coming. The structure maintains its rotation, its patient arrival of light from stars to whatever receives it. The river does not stop. The band does not move from its position in the dark sky. The grain drifts on through the quiet of the interarm region, through the thin cold gas of the local bubble, through the space between atoms that is the dominant condition of the disk. Everything that needed to be said has been said. What remains is what has always remained: the disk, the dark, the light arriving from the stars, and the particular stillness of a night dark enough to receive it all without needing to do anything in return. Rest now. The disk will still be here. Somewhere in the disk, the grain of dust is still moving. No faster than it was, no slower, the same unhurried drift through the same cold space, past the same sparse atoms, under the same light from the same distant stars, that has been crossing the gap for years before arriving at anything at all. The band of light holds its position in the dark overhead, not flickering, not shifting, steady in the way that only very old things are steady, not because nothing has changed within them, but because the changes have been so slow and so continuous that from any single moment they are invisible. The disk turns. Hundreds of billions of stars in the same slow rotation they have been maintaining since before the Earth had oceans, since before the first living thing divided itself in the dark water of a shallow sea, since before any of the elements in a human body had found each other in the same place at the same time. The rotation continues. The light keeps crossing. The grain drifts on.